Great. So, good afternoon. So I just turned in the exams back to you, the graded exams. Please check them and see if everything's okay. I was very satisfied with the outcome of that, with a few exceptions. So let me know if you see any problems with the grading. It'd rather be very consistent in the way things were deducted for the different types of errors. But you know, sometimes we're not perfect. Yes.
What was the average?
I honestly didn't see it. I don't know if you can see it. I posted them on Canvas.
90? I think it's at 90.
It's got to be around there. It's got to be 89, 88, 90, something like that.
Cool.
Okay. So yeah, it's pretty good results. Which should be an indication also of the level of complexity of the third exam would be just about the same. We'll have a take-home portion of that exam. And just be aware of the handouts or the spreadsheets that I post on Canvas. For example, let me go back to the PC. And this is lecture 19 spreadsheet I posted for the lecture last Thursday. And these particular spreadsheet shows what happens with these eigenvalue solution of the two-dimensional problem with right-hand side temperature equal to 1. So that was a problem where all boundary conditions were 0 except the right-hand side wall, which we use a boundary condition of 1. And notice that, well, the series have a very hard time converging, especially at the corners. This is a plot of the temperature on the right-hand side wall. Okay, so I am plotting the temperature at x equal L and for every value of y between 0 and 1. So I'm making L equal to 1. And the situation is that the series has a hard time converging at the corners because there's a jump from 0 to 1. Anytime there's a jump, it's mathematically possible, but physically impossible to have a jump on temperature. So if I notice that I make the value of infinity equal to 100, if I make it a little bit larger than this, then you know the series starts converging a little bit better. But it's always going to present some issues. And if we do a contour plot or a surface plot of these, then you can see that there is some staircasing right there because of the series not converging properly. But in theory, if you evaluate the series all the way to infinity, let me make this 400. Oop, it cannot deal with so many numbers. Let's see, this is too much. Okay, 250. Well, I guess it can only do 200. That might be, let me think. I don't think it's a denominator. I mean, it's not n factorial or anything like that. It's just, maybe it has a hard time converging so many. I don't know why. But anyways, then I solved the same problem. See, there's a jump. The temperature on the bottom wall and the top wall are 0, and then on the right wall is immediately 1. So mathematically, this continues at the corner, at the bottom right corner and the top right corner. And that creates an issue. If you make this infinity number very small, then all these eigenfunctions, let's say we make it 20, these eigenfunctions, see, overlapping on top of each other doesn't actually cancel out to be a flat line. And then if you see this in 3D, this is what you're going to see, which is obviously not correct. So, as I mentioned, the Fourier came up with this technique and actually proved it by evaluating all these series by hand and showing that it actually converges to the right value. Now, if I make that temperature on the right-hand side, instead of being 1, I'm going to make it a parabola that goes from 0 to a maximum of 1 to a minimum of 0. So there's no discontinuity at the corners, but there's still a non-homogeneous condition. So through orthogonality, we find that the constant of integration E on the series is this much. It's just the integral of Fy times the eigenfunction dy, where Fy is this particular parabola. It's a parabola that at y equals 0 is equal to 0, and at y equals lowercase l is also equal to 0. And that one has a much easier time converging. As you can see, it's just basically only using 10 points on the series, it converges to a parabola. If I were to use maybe 5 points on the series, it will still converge to a parabola because it decays much faster. The denominator decays much faster than it's kind of perfect. So I don't have to evaluate all the way to 100, but if I do, then I still get the right solution, and there's no staircasing or ripple effects there on that wall because the series is a very easy time converging. Right, come on. Right. It takes a lot of time to evaluate this one because the constant of integration E is not determined explicitly, it's determined implicitly in terms of these integral. So for every value of n, it needs to recalculate that integral. Okay. So go back to the point. All right. Okay, and as you can see, this is actually much better looking than the previous one. So the spreadsheet is already on Canvas. It's for demonstrative purposes. There's essentially nothing else to see here or change. So we're not numerically approximating the solution of this problem. We're just showing what the series solution looks like. All right. Now another thing that I posted on Canvas was this particular table. Now you notice we solved two problems last week where we form an eigenvalue problem either in the x direction or the y direction, but depending on the combination of boundary conditions, excuse me, let me see, I don't know if I actually pressed the button here. Well, I did. All right, so depending on the combination of boundary conditions, an eigenvalue problem from 0 to L. This is a standard rectangular eigenvalue problem where the second derivative of x with respect to x squared plus beta square x is equal to 0. Beta being the eigenvalues and x being the eigenfunction. All right? So the ones that we solved last week, when the boundary condition on the left, this is the boundary condition on the left and this is the boundary condition on the right, at x equal 0 and at x equal L. When the boundary condition on the left-hand side is the first kind, remember, boundary conditions need to be homogeneous on both sides for this to be an eigenvalue problem. And there's nine possible combinations, right? First kind on the left, first kind on the right. First kind on the left, second kind on the right. First kind on the left, third kind on the right, and so on and so forth, right? This one we solved in class. We found that the eigenfunction is the sine of beta mx, where beta m are the eigenvalues, and the eigenvalues are the roots of this particular function. Sine of beta m L equal to 0. And therefore, beta ml is simply n pi over L, okay? This column right here is kind of the most important one because that is the norm, or the inverse of the norm. Norm being the integral of the square of the eigenfunction, okay? If you take the integral of the square of the eigenfunction, you get 2 over L, or the inverse of that. 1 over the integral of the square. It's hard to see there, I annotated by hand. So this is the actual, remember we take the series expansion, we multiply both sides by the eigenfunction, then we integrate, and through orthogonality we can determine the constant of integration. But what we end up on the right hand side to determine the constant of integration is 1 divided by the integral of the square of these. Okay? So the integral of the square of these when the eigenvalues are these is 2 over L. The integral of the square of these when the eigenvalues are these is 2 over L. And so on and so forth. So we don't really need to determine those by hand. You can use this table. Depending on the combination of boundary conditions you have, you will get a value for the norm, or the inverse of the norm, a value of the eigenvalues, and you don't have to state them explicitly. You just say that the eigenvalues satisfy these roots, and that's it. Okay? So when we're solving a separation of variables problem, and we form eigenvalue problems in different directions, okay? We might have more than one direction where we need to form an eigenvalue problem, especially in 3D or transient problems. you don't need to really explicitly go through the solution process and say, well, the boundary condition on the left is this, and the boundary condition on the right is this, and therefore the constants are these, and the eigenfunction is this, and you don't need to solve for that. You just can reference this table, and that's a solution, okay? We're gonna do some more examples, and we're gonna be referencing this table directly. All right? So, all right, so how do we go about solving a 3D problem? We've done 2D problems with different combinations of boundary conditions, and this is lecture 20. Lecture number 20. All right. 3D problem. Steady. Okay, we're going to do steady later today if we have time. We'll move into transient problems, and you'll see that the procedure is essentially the same. But we're trying to apply separation of variables, and therefore the same conditions and requirements apply. So let's say that we have this. Alright, so in the x direction, this is L, in the y direction, this is L, and in the z direction, let's say this is 1. Okay, we're still satisfying, or trying to satisfy the governing equation, Laplace of t, and this case is of x, y, and z equals 0. So this is steady heat conduction with no generation. So the governing equation is homogeneous, and let's say that the boundary conditions look like t at x equals 0 is equal to 0, t is equal to 0. So this is homogeneous first kind in the x direction. In the y direction, let's say we have t x comma 0 comma z is equal to 0, t x comma L comma z is equal to 0. Again, we have homogeneous first kind on both sides. And on the z-axis, let's say we have t at x comma y comma 0 is equal to 0, t at x comma y comma 1 is equal to, let's say, some TO, some constant value TO. And then this one is homogeneous first kind, but this one is non-homogeneous, and this one we leave towards the end. So z is the non-homogeneous direction. So somehow we need to form eigenvalue problems. So separation of variables applies because there is only one non-homogeneity. Must form eigenvalue problems in x and y, because those are homogeneous directions. Alright? So we start by saying that this is x, y, and z. And therefore, the governing equation, which is the second derivative of t with respect to x squared plus the second derivative of t with respect to y squared plus the second derivative of t with respect to c squared is equal to 0. And that will transform into x double prime of x, y of y, z of z, plus x of x, y double prime of y, z of z, plus x of x, y of y, z double prime of z equals to 0. And if we divide everything by x, y, z, we get x double prime of x divided by x of x plus y double prime of y divided by y of y plus z double prime of z divided by z of z is equal to 0. So now it has the potential to be separated. So let's separate x from y and z. So we have x double prime of x of x is equal to minus y double prime of y of y minus z double prime of z of z. And now x is on one side and y and z are on the other side. So we can use the same argument. If the left hand side is a function of x and the right hand side is a function of y and z, the only way that they can be equal to each other is if they're equal to a constant. We're going to call that constant lambda square. And what kind of sign we're going to assign to it? Negative or positive? If we want an eigenvalue problem in the x direction, we already determined that's a homogeneous direction. We want a, sure, the equation has to be positive, so it has to be negative here. So therefore, when you formulate the equation in the x direction, you have x double prime of x plus lambda squared of x equals 0, and that is an eigenvalue problem. Okay? That is an equation of sines and cosines. That's why you use the negative here. For the x, subject to, what are the boundary conditions in the x direction? Remember, we have first kind. We don't need to go through the separation process. We can already say that x of 0 is equal to 0 and x of L is equal to 0. Right? Both conditions in the x direction are first kind. Therefore, we have x, and both are homogeneous, and therefore we can separate them in x of 0 equals 0, x of L equals 0. Is that clear? All right. What is the solution to this problem? We have an eigenvalue or eigenfunction sine of lambda n x such that lambda n is equal to n pi over L. That's it. So we solve the x direction. Let's look at the y direction. Well, the equation that is left looks like y double prime of y divided by y of y minus z double prime of z divided by z of z is equal to minus lambda squared. Still not separated because the left side is y and z. So now we're going to send the z over to the other side, and therefore that's going to be y double prime of y over y of y is equal to lambda squared minus c double prime of c, c of z. And we're going to make that equal to a constant, because on the left we have y's, on the right we have only z's, and therefore the only way that they can be equal to each other is if they're equal to a constant. We're going to call that constant beta squared. And again, we're going to assign it a negative number because we want to formulate an eigenvalue problem in the y direction. So that in the y direction we have y double prime of y plus beta squared y of y is equal to 0, subject to the boundary conditions in the y direction. They're right here. They're both first kind, they're both homogeneous. So that means y of 0 is equal to 0 and y of small l is equal to 0. The solution of this problem is y of y sine beta m y. I use another index on purpose because this one is independent from this one, such that beta m is also m pi now over small l. This is the problem we're solving. This is the eigenvalues that we end up with. Remember again that eigenfunction is assigned because of the combination of boundary conditions. The general solution to that problem is cosines and sines. Okay? Depending on the combination of boundary conditions, you're going to end up with sine, cosine, or a combination of the two. And the eigenvalue is also a consequence of these combination of boundary conditions. Depending on whether we have first kind, second kind when we impose a derivative, or third kind when we impose derivative, combination of derivative and zero derivative. All right. So now we need to solve for the C problem. The C problem that we have is this one right here. So in the Z direction we have lambda squared minus C double prime of Z divided by Z of Z. And we know that this depends on N is equal to minus beta M squared. Alright, so that is Z double prime of Z, and this will be minus lambda n squared plus delta m squared times Z of Z is equal to 0. So therefore, Z double prime of Z plus delta n m squared Z of Z is equal to 0, such that delta n m squared is equal to lambda n squared plus delta m, this was beta, sorry, beta m squared. All right. So I'm just replacing lambda n squared plus beta m squared into a new index called delta nm squared. All right. And again, this is negative. It's negative, which means that the solution of that problem we have Z of Z is equal to B cosine hyperbolic of delta n m Z plus C sine hyperbolic of delta n m Z. Subject to Z of 0 is equal to 0. That's the only one that we can separate. Out of the original boundary conditions, the only one that we can separate is the homogeneous one. The non-homogeneous one we cannot separate. So that will make B equal 0, leaving Z of Z equals C times the sine hyperbolic of delta n m Z. So dxyz, which is equal to x of x, y of y, z of z, is equal to the summation from n equal 1 to infinity, the summation from m equal 1 to infinity. Notice that this is embedded summations. C and m of the sine of lambda n x sine of beta m y sine hyperbolic of delta n m c, such that lambda n is equal to n pi over L, beta m is equal to m pi over L, and delta n m squared is equal to lambda n squared plus beta m squared. Okay? Now, as we do with separation of variables in 2D, we do the same in 3D. Impose at the end, once you have the general solution, Now you impose the only remaining condition, which is a non-homogeneous condition. Let T of x, y, and z equal 1 equal to T0. On that phase, the temperature is a constant, it's an equal to 0. Then T0 is equal to, well, when z is equal to 1, we have the sine hyperbolic of delta lambda n, or delta nm. So this was n equal 1 to infinity, summation of m equal 1 to infinity, cnm sine of lambda nx, sine of beta my, sine hyperbolic of delta nm. When z is equal to 0, then that ends up that way. Alright? Now again, we multiply both sides, apply orthogonality. Orthogonality of the sine of lambda nx and the sine of beta my. These are two eigenfunctions and they're orthogonal. And what we have is the integral from 0 to L times the integral from 0 to L times d0 times the sine of lambda nx times the sine of beta my. That's what happens on the left hand side. Dx dy is equal to those same integrals on the right hand side. But remember, all of the summations disappear. Remember we went through this exercise? We multiply times these eigenfunction on the right hand side with a different index, and then they will cancel out because they're orthogonal to each other except when n is equal to n. So we have cnm times the integral from 0 to L times the integral from 0 to L of the sine square of lambda nx times the sine square of beta my dx dy, and we have the sine hyperbolic of delta nm. Sorry for punching there. So, then we can separate these integrals. This integral right here is d0 times the integral from 0 to L of sine of lambda nx dx times the integral from 0 to L of the sine of beta my dy. So this one is broken up in two. And that's equal to cnm times the sine hyperbolic of delta nm times the integral from 0 to L of sine square of lambda nx dx times this integral from 0 to L of sine square of beta my dy. Alright? So this right here, this integral right here is what we found on that table. That's the norm of lambda n. It's the integral of the square of the eigenfunction, and that's equal to L over 2. You'll see it on the table inverted. Why do you see it inverted? Because once you send it to the left hand side, you need to solve for C and M. It will be in the denominator. And this one is the norm of beta m, which will be also, in this case, L over 2. From table. Alright? This one right here, the integral of the sine of lambda nx, when lambda n is n pi over L, Remember, that was 1 minus 1 to the power of n. We did this last week. And this one right here happens to be 1 minus 1 to the power of m. Divided by lambda n, and this one divided by beta m. Yes, I was missing that. All right. So we have t0 times 1 minus 1 divided by lambda n times 1 minus 1 to the power of m divided by beta m is equal to Cn m times the sine hyperbolic of delta n m times L over 2 times L over 2. And therefore Cn m is equal to 4 t0 times 1 minus 1 to the power of n, 1 minus 1 to the power of m, all of these divided by beta m lambda n L times the sine hyperbolic of delta nm. And that is a constant of integration that goes into the series summation. All right, so it's just essentially the same implementation of the technique. It's just it goes over a few other tricks to get to the final answer. And again, this can be evaluated the same way we just did it on MathCAD. Just impose an infinite number. This is the solution, evaluated at any value of x, y, and z. And in this particular problem, we're also going to have a jump, so that series is going to have some hard time trying to converge. There's 4 jumps on this problem. If you look at the original problem, we have a temperature jump at z equal 1. Right on the top face, everywhere is on every face the temperature is 0. On the top face, the temperature is T0. So on all this top edges, the temperature jumps from 0 to T0. And that creates some problems. All right. So this is a method of separation of variables. It's pretty straightforward. And again, depending on the combination of boundary conditions, we use that table to just say what the eigenvalues are and the eigenfunctions and the norm. Norm, remember, being that integral of the square of the eigenfunction. All right. Now, what happens if there is more than one non-homogeneous condition? We said that separation of variables only works if there's only one. You can see why. Separation of variables does not apply directly. Instead, use superposition plus separation of variables. All right, let's look at an example to see how this works. It's actually quite simple. So let's say that we have superposition plus separation of values. So let's say that we have the same problem that we've been looking at, and it's a rectangle, big L, small l, and inside the rectangle we have the Laplace of t, which is a function of x and y only, is equal to 0. So steady heat conduction with constant conductivity and no generation. And here we have t equals 0, and here we have t equals 0, here we have t equal 1, and here we have t equal 1. Now we have two non-homogeneous conditions. If we want to formulate this mathematically, the governing equation looks like Laplace of t is equal to 0. And the boundary conditions, they're all first kind. So t at 0, comma y is equal to 0. T at L, comma y is equal to 1. T at x, comma 0 is equal to 0. T at x, comma L is equal to 1. So as you can see, this is non-homogeneous direction. First kind. This, the y direction, is also non-homogeneous, and it's also first kind. So, the principle of superposition basically states that since we're dealing with a linear problem, if we have one solution to that linear problem, one general solution, and we have another general solution to that linear problem, and we can add them up, and that will be a solution as well. So we can pretty much say, let t of x and y be equal to t1 of x and y plus t2 of x and y. And if that's the case, then the governing equation, which is Laplace of t of x and y, is then equal to the Laplace of t1 of x and y plus the Laplace of t2 of x and y, which is equal to 0. Right? So this is arbitrary. We're going to say that dx and y, we're going to break it up into 2. And that's only possible. So the governing equation introduces into this because the governing equation is linear. And all boundary conditions are also linear. Well, first kind conditions do not have to be linear, they're just first kind, but second kind condition is the first derivative, it's a linear operator. And third kind condition, the same thing. So then, is this step here understandable? Right? The governing equation is this. And since t is t1 plus t2, then I can break it up into 2. I don't need to go over the demonstration of the Laplace of t. If t is t1 plus t2 can be broken up into 2 because they're just derivatives, and you know the derivative of the sum of two functions is equal to the sum of the derivatives of the function. Okay? So, and the same thing applies to the second derivative in any direction. So this is true. All right. So now we're going to arbitrarily let the Laplace of t1 is equal to 0. That's arbitrary. I don't need to say that. All I know is that the Laplace of t1 plus the Laplace of t2 is equal to 0. Right? That's all I know. But I'm going to arbitrarily say that this is equal to 0. If I say that this is equal to 0, then this one must be equal to 0. This is not arbitrary anymore. If I make this one equal to 0, then this one has to be equal to 0. If I make this one equal to minus 1, then this one has to be equal to plus 1 for them to add to 0. Now, I'm not going to make the problem complicated, I'm just going to make it homogeneous. And then basically this problem is broken up into 2. from this one, t1 of 0, comma y, I'm going to make it 0, and therefore t2 of 0, comma y must be equal to 0. If you look at the original conditions, t at 0, comma y was equal to 0. Since t is the sum of t1 and t2, if I make t1 equal 0, then t2 has to be equal to 0. t1 at L, comma y, I'm going to make this one equal to 0. Then t2 at L, comma y has to be what? Huh? 1, right? I'm going to make t1 at x, comma 0 be equal to 0, therefore t2 at x, comma 0 must be. And then if I make this one equal to 1, then t2 must be equal to 0. And that's it. Now I have two problems that can be solved using separation of variables. Solve for t1 using SOV and solve for t2 using SOV. Such that t1 of x, comma y is equal to the summation from n equal 1 to infinity of an sine of lambda n x sine hyperbolic of lambda n y such that an is equal to 2 over n pi sine hyperbolic of lambda n L 1 minus 1 to the power of n such that lambda n is equal to n pi over L. I don't need to go through the entire process of solving this problem because we already did. That's a simpler version where the homogeneous direction is x, the eigenfunction is sine, the non-homogeneous direction is y, so we get sine hyperbolic. And after applying the last non-homogeneous condition, we get this. All right? T2. En, this will be sine hyperbolic of beta n x times sine of beta n y such that Bn is equal to 2, 1 minus 1 to the power of n pi, and this will be sine hyperbolic of beta n L such that beta n is n pi over small l. Problem solved. All right? So one of these will yield this problem with the discontinuity on the top wall. Okay? Temperature jumps to 1 on the top wall. The other solution, the other series solution will yield this one where we have a discontinuity on the right hand side wall. When we add these two series together, notice that these are not embedded summations. These are separate series. That's why I can use the same index on both. When we add them together, what happens? We get a discontinuity on the top and a discontinuity on the right. And if I make infinity infinite enough, those discontinuities should actually flatten out to exactly 1 and 1 on the top and on the right. Okay, so that's superposition. It's just a little handy trick that we play when we have more than one discontinuity. But the method itself is separation of variables. Any questions? All right. So, what if the discontinuity, the non-homogeneity, is on the governing equation? What if the governing equation is non-homogeneous? For example, or for instance, in steady heat conduction with internal energy generation, UG triple prime. So let's say that the domain itself where heat conduction is occurring, there's some sort of chemical process or there's resistances inside that are inducing an energy density. Energy per unit time, per unit volume. Okay, joules per unit time, watts per unit volume, watts per meter cube. Right? So the equation looks like this. That would be the divergency of the thermal conductivity times the Laplace of the temperature, times the gradient of the temperature, plus UG triple prime is equal to 0. And this is a constant value of generation. Okay, generation can also be a function. Such that UG triple prime is in units of watts per meter cube. Is power density or energy per time density. Okay? Now let K and UG triple prime be constant. So let's say that the domain has constant thermal conductivity and the generation term is also constant, it's not a function of space. Then if K is a constant, we can take it out and divide everything by K. So we end up with the Laplace of T plus UG triple prime over K is equal to 0. Or sometimes expressed as U0 is equal to 0. And this is known as the Poisson equation. No longer Laplace equation, now it's a Poisson equation. It's just a Laplace with it's a non-homogeneous Laplace basically. All right, so let's look at an example. That's for instance, how you would end up with a non-homogeneous condition, or a non-homogeneous governing equation. If you have steady heat conduction with internal energy generation. Okay, it would happen on every field of engineering and science. There's cases in which you have a forcing term, a field function, or a field constant in this case, that will induce non-homogeneities into the governing equation. Now, these governing equations being non-homogeneous means that the problem need not be driven from the boundaries. Okay? Remember that at least one boundary condition needs to be non-homogeneous for the solution to be non-trivial. Okay? If the equation is homogeneous and all boundary conditions, whatever their kind, are homogeneous, the solution is 0. There's no other way. Okay? If one of the boundary conditions, at least one point, is non-homogeneous, that's what drives the entire problem out of 0. Okay? In this case, because the governing equation has an internal generation, as a non-homogeneous term, the equation itself drives the problem. So the boundary conditions need not be non-homogeneous. So I can give you an example where, for instance, we have, again, let's make it a rectangle, L by L, and internally we have this, and let's say that the temperature is 0 everywhere. Okay? So what do we expect out of the solution of this problem? Well, since we have internal generation, that internal generation is constant throughout the domain, it's the same thing on every corner or in the interior of the domain is the same, but we expect, if this is positive, we expect the temperature to grow internally. But since the boundary conditions are forcing the temperature to be 0 at the edges, this whole thing is going to produce a maximum temperature right at the center. Right? It's going to grow at the center, it's going to be kind of radially symmetric towards the center, and when it approaches the boundaries, it's going to decay to 0. And that's a final equilibrium solution of this problem. Okay? Well, how do we find it? Well, technically, separation of variables should apply. Again, the governing equation looks like the second derivative of t with respect to x squared plus the second derivative of t with respect to y squared plus q0 is equal to 0. And the boundary conditions look like t at 0, comma y is equal to 0, t at l, comma y is equal to 0, t at x, comma 0 is equal to 0, and t at x, comma l is equal to 0. So technically, we have a single non-homogeneity, and technically, separation of variables should work directly. However, that's not the case. If you try it, you will get stuck trying to apply the non-homogeneous condition of something. Here, it seems that we need to build a first kind homogeneous, and this is first kind homogeneous on both sides, in both directions. So it seems that we need to build eigenvalue problem in the x, and eigenvalue problem in the y, and then apply this condition at the end, but it's not really a condition, that's part of the equation. So, even though there is only one non-homogeneity, separation of variables does not apply directly. Instead, try a superposition for example, that t of x and y be equal to theta of x and y plus phi of x, for example. Or you can make it phi of y. So you're going to break this up into a function of x and y and a function of x. This is one that could work. We don't know. So the governing equation says that the Laplace of t of x and y, which we can translate it, or plus q0, is equal to the Laplace of theta x and y, plus the Laplace of phi is simply the second derivative of phi with respect to x squared, because phi is only a function of x, so it makes no sense to say Laplace. It's just a second derivative with respect to x, plus q0 is equal to 0. Right? So the governing equation, which was this, can now be broken up into this. And now, try this, and now let the Laplace of theta is equal to 0. If we let the Laplace of theta equal to 0, then what would happen with the second derivative of phi plus q0? What would that be? Equal to what? This is the equation, and I make this one equal to 0, then this one plus this one be equal to 0. Alright? right. So remember, this one plus this one and this one are equal to 0. T is equal to theta plus phi. So what about the boundary conditions? I'm going to say if theta 0, y is equal to 0, then what is phi of 0? 0, right? Because they both have to add up to 0. If theta of L, y is equal to 0, then what would be phi of L? 0. Now here's the tricky part. How much is theta of x, 0? At y equals 0, how much is theta? Can I really make that 0? If I make this one 0, when y is equal to 0, I'm basically saying that phi of x is equal to 0. Phi cannot be evaluated at any value of y because it's not a function of y. So if I make this one at y equals 0, I'll make this one 0, and I know that t of x and 0 is equal to 0, then phi of x will be 0, and we cannot have that because that's trivial. If we make that 1, then phi of x is going to be minus 1, so we're forcing phi of x to be a constant. That's not possible either. How about theta of x, 0 is equal to minus phi of x? That's our only choice. This one is 0, at y equals 0. So theta of x, 0 is the negative of these. It's 0 minus phi of x. And theta at x, L is going to be minus phi of x. Is that clear? Okay, that step can be confusing, but that's the only choice we have. Remember, the function phi is not a function of y, it's only a function of x, and therefore we cannot force it to be anything. Alright, so that means that, well, the problem for phi is solvable, right? It's a 1D problem with homogeneous conditions. It really doesn't matter, it's just a 1D problem. But we need to solve for phi in order to solve for theta, because phi is a boundary condition for theta. See? So we need to solve for phi of x to be able to solve for theta of x and y. So the problem in phi looks like the second derivative of phi with respect to x squared plus q0 is equal to 0, subject to what is the solution of this problem? Let's see if you can see this. That's sines and cosines? Is this an eigenvalue problem? No, right? Because we're missing the phi here. Okay? So how do we solve this problem? We integrate. This is a constant. Right? So we basically integrate and we say that the phi dx is equal to the integral of minus q0 dx, right? And then therefore phi of x is equal, the phi dx is equal to minus q0x plus c1. And therefore, phi of x is equal to the integral of minus q0x plus c1 dx. And therefore, phi of x is equal to minus q0 x squared over 2 plus c1x plus c2. Alright? So, such that phi at 0 is equal to 0, and that would be minus q0 times 0 squared over 2 plus c1 times 0 plus c2. That means that c2 is equal to 0. Right? Such that phi at L is equal to 0, and that will be minus q0 L squared over 2 plus c1L, and therefore c1 is equal to q0 divided by L over 2. So when we plug these two in here, we find that phi of x is equal to q0x divided by 2 times L minus x. And there you have it. That satisfies these equation. This is the second derivative of these with respect to x squared is equal to minus q0. And it also satisfies the two boundary conditions. At x equals 0, you get 0, and at x equals L, you get 0. Alright. So now we have that parabola in the x direction. And now we need to solve the problem of phi, of theta. Such that the governing equation looks like the Laplace of theta is equal to 0, and the boundary conditions look like 0, comma y is equal to 0, L, comma y is equal to 0, x, comma 0 is minus phi of x, x, comma L is minus phi of x. What do we do with these problems? We have to use superposition. So, superposition, let theta of x and y be equal to theta 1 of x and y plus theta 2 of x and y. Oops. And therefore, right? So now we're going to have one problem where these is going to be the only non-homogeneous condition, everything else 0, and the other problem where these is going to be the only non-homogeneous condition. So, such that phi 1 of x and 0 is equal to minus phi 0 of x, and such that phi 2 of x comma L is equal to minus phi x. The rest 0. So, solving, and this is the last step of this problem. P1 of x and y looks like the summation from n equal 1 to infinity. These are all first kind boundary conditions, so we should end up with sines and sine hyperbolic. So this will be Cn times the sine of lambda nx times the sine hyperbolic of lambda n times y minus L. Such that Cn is equal to 2 over L times the integral from 0 to L of whatever this function phi of x is times the sine of lambda n x dx times 1 over the sine hyperbolic of lambda n L. Right? And such that lambda n is n pi over L. And theta 2 is equal to summation from n equal 1 to infinity of dn sine of beta n x times the sine hyperbolic of beta n y such that dn is equal to 2 over L integral from 0 to L of minus phi of x sine of beta n x dx 1 minus or 1 over sine hyperbolic of lambda n. This should not be lambda n. It should be beta n. Beta n. L. Beta n. L, yes. Such that beta n is equal to n pi over L. Same thing. Okay. So we can use this separation of variables in combination with superposition to solve all kinds of problems with all kinds of combinations of boundary conditions, with all kinds of combinations of non-homogeneities. All we have to do is methodically apply it so that every time we break it up, we end up with a simpler problem. And the simpler problem we end up with has to be a problem with that governing equation is homogeneous, all boundary conditions are homogeneous but one. And we can have as many of those as we want because we can always solve those by separation of variables. Alright, any questions? Alright, that's it. So let me know again if you have any questions about the test. Those of you who came in late, come back to me and I'll give you your exam. And I'll see you on Thursday.